5, 6, basically a bunch of word problems, and I just renamed it. They said applications and models, which is really just over exponential growth and decay, and then also compound interest. Okay, we have population growth can be modeled by the function, P of t equals P sub 0. P sub 0 just always means your initial anytime you see a sub-zero, times e to the kt, and k has to be greater than 0, just kind of for our function. So this is our initial amount, initial population, K is the rate at which it's growing, the constant at which it's growing, which is called the exponential growth rate. That's a P. So you have your initial population, your exponential growth rate. The t is basically your variable, so think about it like your x. And then we will plug in different amounts to find out different things. So the first example, I'll just read it. It's on page 450 in your book. It says, in 2009, the population of Mexico was about 111.2 million. So that's important. And the exponential growth rate was 1.13% per year. So also, the amount of time that it tells you is usually fairly important. So the first thing that it asks you to do is find the growth function. So that means I'm going to make this P of t. So P of t is equal to the initial amount. So the initial amount is 111.2 times E. Our K is, however, not 1.13. We have to write it as a decimal, which is going to be 1.0113. So I have 0.0113 times t, all in my exponent, and that would be what my function will look like. And then I will also be asked to estimate the population in a certain year. I always like to make a little note when I actually write my equation. T is years since my original year. So T is years since 2009, because that's what I read in the problem to you guys, so that's kind of hard to see. So part B, estimate it in 2014. So in 2014, I count how many years have passed. So 5 years, which means that I am going to do P of 5 equals 111.2 times e to the 0.0113. When you do this, make sure that this entire thing is still in your exponent, so times 5. So make sure, even if you have to do carets, that you have parentheses around everything in that exponent, and this is times, not subtraction, just in case it looks confusing. And then I figure out what that is. I do that on my calculator, and as long as I type in those parentheses, I should be able to do everything in one step, and you will get 117.7. Remember, this is in millions of people, so that seems reasonable to me that a population has grown by about 6 million. Then another piece of the question is, how long will it take for the population to double? So sometimes those are weird ones. I'm going to write out just how long to double. And so that's where our actual everything that we've been doing kind of comes into play. So I know what my initial amount was, so how much is double is it? So 2 times initial equals, so 111, that's easy to double, not 3. How about 222.4? This is going to be my P of t. That is the piece that I'm looking for. I am plugging it in for that. because it asks how long to double. So I'm actually going to plug in that amount. So I have 222.4 equals 111.2 times e to the 0.0113t. I'm going to scroll this down a little bit. Then I'm going to divide by 111.2. 111.2. I shouldn't actually have to do that division. I should just be able to say 2 equals e to the 0.0113t. And then I'm going to use all the skills that I've just been using in the last chapter to actually solve this. And I can take the natural log of both sides. You can do a few different ways. But right now I'm just going to take the natural log of 2 equals the natural log of e to the 0.0113t. The natural log of 2, I don't know what that is yet, so I'll write the natural log of 2 again. The natural log of e will just kind of go to nothing. I don't know what to say for that one, sorry. And I will just be left with my exponent, which is 0.0113t. And then whenever I get my calculator, I will do this division all at the same time. So I'll divide by the 0.0113. And then to figure out what t equals, I will just plug in the natural log of 2. And I will divide that by 0.0113. So I'm typing this into my calculator. And I know a lot of people had problems when they were, or I don't know about a lot of people. I know somebody had problems typing stuff into the calculator. So when you type it in, make sure that if I look right here, that I actually put a parentheses in after that natural log of 2. I'm going to press enter, and I should get 61.34. So then what I had somebody do was take the natural log of 2 divided by 0.0113. And that's going to give you not the right answer. And that's because what it's actually doing, if I were to like try to pull this over, let's see how it worked. Oh, it worked out pretty good. So when I look at this, what the calculator is actually doing, which is not what I want it to do, but it is actually taking the natural log of this whole thing right here. So this is just absolutely not what we want to do. Make sure you put in this parentheses. This is a very, very important parentheses. The other way to solve this in your calculator, let me make sure I don't have anything in my y equals. So I'm actually going to type in, I want to see how long it takes to double. Since I already figured out what my doubling amount was, it was 222.4. You still have to figure that out. And I'm just going to make that line on the calculator. And then I'm also, sorry, I have lots of stuff typed in. I'm also going to graph the other side of my equation, which was 112, another one sometime, 0.2, times e, so e to the x, so second natural log, whoops, second natural log, it didn't like my second, still doesn't like my second natural log, so e to the 0.0113x, because it's just going to do x no matter what you tell it to do. Okay, so what that is going to do is when I look at this graph, it's going to give me something and be like, hey, there's nothing on my graph. That's awesome. So maybe it will stop doing this. And that's actually just something really old. That's not actually what I want it to look at. What I actually want it to look at is I can go into my window. Okay, so this is something like I would expect to see on my calculator if I had nothing but those two things that I plugged in. I don't like my zoom. I'm not going to make you do tons of find the window kind of crap because it's really hard sometimes to figure that out when that's not at all what I actually want to find. So I'm going to scroll down my zoom menu, and what I want it to do is figure out where it fits. There's one that says fit. So that one says zoom fit. It's my option 0, and I can press enter. Or if I know exactly what I want, I can just press enter. Okay, so it should have picked, and it should have put both of those on my graph for me. So I can hit my trace button now. And so if I look at this, my trace is at 222.4. and then I can scroll up and down between the different lines. So it tells me what line it's on up here in this top menu. So that's this bottom line down here. However, I still can't see when they cross. So now I'm going to go into my window and I'm going to change my X max, because if I look back at my graph, it was kind of, if I look back at my graph right here, I want it to go further to the right because it looks like they'll cross somewhere over here if I'm looking at this bottom graph. So my X max, I don't know, let's say 50, because that's generally what I do, is kind of just guess and check and find something that'll work for me. Okay, if I look at it again, I'm pretty close. It looks like it's getting pretty close to touching. It hasn't actually touched yet, so let's go change our window again. So then we'll do window maybe 100. I'm just going to type in 100. And I really would like to see a little bit higher than that top line. So I'm going to go ahead and I'm going to change it to like 250 just so I have nice round numbers. It doesn't really matter. Sorry. So now hopefully I should be able to see where they cross. So this is the second way to actually solve this. You can do everything out by hand, but sometimes it's nice just to check your answers and actually see that, oh yeah, they do happen to cross right here. So I could trace and I could kind of eyeball when I thought they were close. So right there, it kind of looked like it was crossing if it would have stopped moving for me. Maybe one or two more. And so that's 62-ish. That's pretty close to 61-ish. If I wanted to know exactly and I wanted the calculator to actually do it for me, I could do second trace because that says calculate up there, or it's your calculate menu. I want to find the intersection, which is option 5. I can hit 5 or I can scroll down and press enter. My first curve, I can't really tell which one it's on, so I'm going to use my left and right arrow. I'm going to hit enter when I can tell that it's on one of them, and then it'll automatically jump to the next one. I'm going to hit enter again. I'm going to guess, and I'm going to press enter now. 61.34. Congratulations, we've done it. Okay, so the previous equation that I gave you will be the same equation I use when interest is compounded continuously. I will use this p sub 0 e to the kt. This will still be my initial, instead of population, it will be money amount. Exponential growth rate, that will be just my APR. Okay, so let's do a money problem. I just like always having my actual formula right there. So P of t equals P sub 0 e to the kt. I'm going to read you a problem. It says suppose that $2,000 is invested at interest rate K, compounded continuously, and grows to 250465 in 5 years. So these are both dollar amounts, and this is my interest rate. What I'm asked to do is actually find my interest rate. Okay, if I wanted to write a little equation out for it, I'm going to basically put pieces in for this. This will be my P of t, that's the actual amount. The 2,000 is my P sub 0. K is what I'm looking for, and 5 years is my time. Compounded continuously tells you that you're going to be using your E. So now I'm going to plug these into my equation. So I have 250465 equals, my 5s are not working out for me, equals 2,000 e to the k times 5. Okay, you could write 5k, that doesn't really matter. I'm going to divide both sides by 2,000. We're just going through and solving this. 2,500 divided by 2,000. So I have oops, this is not where I want it to be. I have 2504.65. Whoops, divided by 2,000 will give me 1.252. 1.252 equals e to the k5. How I solve this is I take the natural log of both sides. I'm just going to try to squeeze it in there. Then I'm going to take the natural log. I'm going to do the natural log of 1.252. When I take the natural log of this side, I will just be left with 5k. the natural log of 1252. The natural log, I'm going to use my second answer function. So second, the negative sign here on your calculator says ANS is your answer. And I will press enter and gives me 0.225, 0.225, and then I'm going to divide that by 5. And I will get basically 20, no, 0.045 equals K, which if I said you will earn a 0.045 interest rate, everybody's like, oh, that's absolutely awful. Even that's pretty much what some of the things sound like. So make sure you actually change things to a percentage. So K, we're really going to say equals 4.5%, because that's just how we're more used to hearing things. Okay, I might also ask you what the value will be in 10 years. In 10 years, which means basically just 10 years from the starting date. So I know my function, I know what my function here will be now because I know my interest rate. So I can rewrite my formula. So I have P of t equals 2,000 times e to the 0.045t. Then I asked for the value in 10 years, so I'm going to do P of 10 equals 2,000 e to the 0.045, I forgot my 5, times 10. What I like to do is do the 0.045 times 10 first. It doesn't matter. You can plug this straight into your calculator and get that the P of 10 should be equal to $3,136.62. If you wanted to throw in a dollar sign, you could. And then I have some things grow and just keep growing and growing and growing forever. But then we actually have more like real life situations that don't actually do that. And those are called logistic functions. This is not like an official name or anything. But it's really what actually happens with populations is that it might look like they're growing exponentially, but eventually they're going to kind of level off because each habitat can only support so many things. So what happens is we get a function that looks, we're using P of t for everything because it just represents population and time. Those things really don't matter. The generic formula for this is a over 1 plus, my pen just started going crazy, b times e to the negative kt, sorry about that. So what happens with populations is I basically have some horizontal asymptote that it actually doesn't cross, even though some horizontal ones it can cross, but these ones won't. And I will get some sort of population evening out, and it'll look more realistic than what sometimes happens. So P of t, so I'm going to read you a problem on page 455, and it says a lake is stocked with 400 fish of a new variety. The size of the lake, the availability of food, and the number of other fish restricts the growth of that type of fish and this lake to a limiting value of 2,500. Limiting value of 2,500. Okay, and then the next rest of the problem, the population gets closer and closer to this limiting value but never reaches it. The population in the fish after in the lake after time t in months is given by this next function, which is P of t equals 2,500. Whoops, that didn't work out very well. 2,500 over 1 plus 5.25 to e, I'm writing really sloppy, times e to the negative 0.32t. Okay, so most of the time they'll probably give it to you. Anyway, the limiting value is that starting number, the rate, and probably your initial population. I'm not completely sure where this B comes from. Anytime I've actually done this is we've had to create these equations, which is actually really, really, really hard when we're doing modeling stuff. But they're really fun to work with if we had more time. So it might ask you what the population is at a certain time. So they come up with this amount. So P of 0, that should be my starting amount. And just from the problem, I know that it is stocked with 400 new fish. So hopefully I would get out 400. So I'd do 2,500 divided by 1 plus 525 e to the 0. It doesn't matter what that the 3, 2 is there, because anything to the 0 is just going to be 1. So this will be times 1, and then it will be 1 plus 525 will be 625. And I'm being really sloppy here and erasing my work, which I never want you to actually do. And then 2,500 divided by 625 is 400. So that's just, it might just ask you for different populations. If it tells you that it's limited by a certain amount, it'll probably hopefully give you those equations, but you should be able to kind of figure those out. Okay, the other type, I will just give you another type of limited growth. We're not going to worry about doing an example of them, just so that you're familiar with the actual formulas that you'll be using, because I think you guys should be able to solve kind of whatever you're given. I have L times 1 minus e to the negative kt, and k has to be bigger than 0. And something that's going to look like is my horizontal asymptote will be here, and it will grow just steeper like that. So it'll grow like from like right here, that'll be your initial amount, and it'll grow like that. Whereas this one kind of grew a little bit kind of slow and then really fast, and then it evened off. Different types of populations grow in different ways. So, okay, everything that we've talked about so far has been growth. Money grows, populations usually grow. But now we're going to go towards decay, an exponential decay. So when I do like a normal picture of exponential growth, it's gonna just kind of grow like that. An exponential decay is gonna die really, really fast, and then it starts slowing off and things are not dying as much, basically because there's not as much to die. What happens is the different types of formulas. So for growth, it was just P of t equals P sub 0 e to the kt. For decay, the only thing that's going to change is it'll still be P sub 0, and it'll be e to the negative kt. So as soon as I see a negative sign, it's decay. That just means I will have something that looks more like this. So where this is useful is we'll actually find the decay rate and the half-life formulas. So, or I'll give you them formulas and we'll find those different things. So decay rate and half-life. So if you guys aren't familiar with half-life, that is how they carbon date things like from the dinosaur age to tell how long ago kind of things. You can use it for anything. It doesn't have to be the dinosaur age. So K is the decay rate. So they kind of have their own little variables. And half-life is T. So think half-life is time, usually, is how it's, or that is how it's measured, and not usually. So my formulas, they have them just kind of already solved for you. They're all the same formula. They're all derived from the same formula. But they will be K times T equals a natural log of 2. Half-life is we're dividing by 2. That's where the 2 kind of comes from. Okay, another way to write the same exact equation, if I am looking for my decay rate, it will be K equals the natural log of 2, all divided by T. If I'm looking for my half-life, I can set it up like this. So I have T equals the natural log of 2 divided by K. Okay, I basically have these two things will Just always, this is just my generic equation, and I just use it for whatever I'm actually solving for. So an example of that is a radioactive element, carbon-14, has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered a linen wrapping from one of the Dead Sea Scrolls that had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? Okay, so the first thing I have to do is find the decay rate. I'm not going to use the 22.3% for a little bit. So the first thing I do is find my k. So I'm going to write out k equals the natural log of 2 divided by 5750. I'm going to do that in my calculator now. And I have the natural log of 2, remember to put in that parentheses, divided by 5750. And that equaled 1.2 times 10 to the negative fourth. So if I write that out, I'm just going to write it out like that, which really means 1, 2, 3, 4. So I have 0.00012 is what my k equals. You could probably write it out cleaner than that. Now we're going to plug this into our function that we already know up here, basically this decay, and my carbon-14 formula, if I'm told that I'm using carbon-14 dating, I can write P of T equals whatever my initial amount was times e to the negative 0.123012 times t. You can use this now for any carbon-14. Okay, then I'm going to do plugging in values I know. So I know that I've lost 22.3%. So if I've lost 22.3%, it's the same as having 77.7%. So you would just do 100 minus 22.3 to get the 77%. And this is my P of T. The percent that you have is your P of T, the percent you have. And some of these are a little bit strange, but we'll work through them. So the percent you have is your P of T. So I'm going to go ahead and write it as 77.7% equals P sub T. We're looking for, I believe we're looking for our time. So it seems kind of weird because we're not ever really given an initial amount. But the weird thing is that when I'm talking about percent, my initial amount is always 100%. So I'm going to replace the P sub 0 with 100%. I should have wrote out a percent over here. I'm being sloppy. So 100% is the same as 1. So I'm going to rewrite my decimals so that I don't have percentages anymore. And I have 0.777 equals 1 e to the negative 0.00012t. Forgot my point. I don't actually have to divide by 1. However, I will just for the sake of doing it. So if I divided by 1, and I would just be left with all this stuff. So the 0.77 and this e side. I'm going to then take the natural log of both sides. When I take the natural log of 0.777, I get negative 2.5. It's spazzing out. Oh my gosh. Negative 0.25. The natural log of e will just be 1. Will just give us that exponent, so negative 0.00012t. And then I will do this division, 0.00012. I just want to finish. I'm going to do that division. I'm not going to write it all out. Maybe I will. and then it's a negative as well. So when I do that division, I have just 0.25 divided by 0.1230, 1, 2. I'm not worried about my negative signs because you should know your negative rules. And I get 2083. 2083 equals my t, which is not exactly what they got because of rounding errors. So I rounded. If you actually just plug in everything in your calculator all at the same time, you won't have rounding errors. But if I look at the answer in the book, I have 2,103, which is actually pretty close to this amount. So the further you're taking out your rounding, the less problems you'll have. So that's just a good example of don't actually do rounding. Okay, so we should have got 2013 equals t, and they do say about equal to t. So they even realize that they have rounding errors because rounding errors happen in real world problems. But this should be basically everything you will be able to do in the next problem or in the next section. So remember that you can use this formula for anything that says carbon 14. I want you to do work on page 459, and I want you guys to do numbers 1 through 21 odds. Okay, so you will be able to check all your answers, but if you do not understand how they got to some of those answers, you better be checking with me, okay? So we'll see you tomorrow.